Yeah. So here they say we have hydrated potassium carbonate, which is K2CO3. And when they say it's hydrated, they mean that it is bound to a certain number of moles of the water of crystallization. That's the concept you did in grade 10, the water of crystallization. You used to say it's the water that is stoichiometrically bound into a crystal. Well, this means that maybe let's say you have a salt, a crystal, because the salts, you see them as crystals. Well, they do have a certain amount of water in them that is bound in a crystal lattice. So that salt becomes a hydrated salt. It doesn't mean it's in aqueous solution. No, it's just the water that is trapped inside of this ionic crystal lattice. Everything I'm saying to you is grade 10, so you probably forgot about that. But it's not really important now. So we have hydrated potassium carbonate. They tell us that it is a weak base. A solution is prepared by dissolving some of this solid into water. And now they say write down the name of the conjugate acid of the carbonate ion, which is the CO3 2-. So does anyone know what is the conjugate acid of this carbonate ion? You can just go ahead and turn on your microphone and tell us. Okay. No, no one has an idea, so we'll just pass it. That's fine. Now, next they say a hydrochloric acid solution having a concentration of 0.1 mole per cubic decimeter is titrated with the prepared potassium carbonate solution having an unknown concentration. The balanced equation for the reaction is given to us as follows. We have 1 mole of potassium carbonate reacting with 2 moles of hydrochloric acid in order to produce 2 moles of potassium chloride, 1 mole of carbon dioxide gas, and 1 mole of water. The results of the titration are given below in this reaction. In fact, a table, sorry. So here we can see that 2 experiments were performed. Run 1 is actually experiment 1, and run 2 is experiment 2. In both of these experiments, they tell us that they used 25 cubic centimeters of hydrochloric acid. But in the first experiment, they used 20.05 cubic centimeters of potassium carbonate. In the second experiment, they used 20.15 cubic centimeters. 2 different volumes in 2 different experiments. Okay. But now they say this is the volume of potassium carbonate in burette. Yeah, a burette. A burette is that instrument in which they have filled the potassium carbonate, and then they'll be turning on that thing that looks like a tap. And then the drops of potassium carbonate will be coming out of the burette, maybe into the beaker or the Erlenmeyer flask that has the acid. But I want you to see what is happening here. They say initially in the burette, we had 6.5 cubic centimeters. Now we want you to tell us how much will be there when the reaction has stopped? If it is given that we used 20.05 cubic centimeters. Yes, initially we had 6.5, but we used 20.05. So how much do we have finally in this burette? Well, how do you determine this P? Well, easy. You just say 6.5 and you add it to 20.05. Then you get 26.55. Because you can see clearly that the volume of potassium carbonate is actually increasing. Yes. How is it possible for us to use 20.05 if we only have 6.5? Well, it's not possible. So it means we just take this 6.5, we add it to 20.05, then we get the final volume. In the second part of this, the second run, they tell us that they used 20.15, but the final volume will be 48.3. So how much was initially there in the burette? I've given you a hint on the first one. So what do you think on the second one, Garabo?
So I'm not sure, but I think it's 28,15 because I minus the final burette reading with the volume of the potassium carbonate used.
Okay, no, you are right, Austin. 200% correct. Yes. You just had to say 48.3 minus 20.15, and then you get the initial volume, which is 28.15 cubic centimeters. But I just want to make it clear that these two volumes, those that you see under that, the initial and the final volumes, it's not what you'll be using in your calculations. In your normal calculations, you'll be focusing on the 20.05 as well as the 20.15. All right. So we have told them the value of P as well as the value of Q. Next, they say to us, methyl orange is used as the indicator. Explain why methyl orange is the most suitable indicator for this titration by referring to the pH at the equivalence point. So, do you have any idea on this one, Hlekani?
No, sir.
Oh, you don't have any idea. What about you, Garabo? Do you have something?
No, sir.
Okay. Well, this is the reason you had to know here to say when do you use each indicator. For instance, the methyl orange, we use it every time when we titrate a strong acid and a weak base. The bromothymol blue, we use it every time when we titrate a strong base and a weak acid, so that the final solution will be basic. The phenolphthalein, I don't think I'm getting my indicators right. I don't know. But I'm just a tutor, guys, so they shouldn't be in my head. But you are a learner. They have to be in your head. So you have to go and study that table. Okay, I think I can still get them right, you know. Yeah, I think I can still get them right because there's only three that you need to be worried about. It's the methyl orange, the bromothymol blue, as well as the phenolphthalein. Yes? No, no, yes, those are there. Okay. I think the bromothiol blue, you use it when you have yeah, I know, I don't know. I forgot. But they have to be in your head. So, well, for this one, that's the reason. Because here we can see that hydrochloric acid is a strong acid, potassium carbonate is a weak base. So the resulting solution here will be acidic. But then how do you answer this formally? Well, you have to tell them that this is the reaction between a strong acid and a weak base, and therefore, at the equivalence point, the pH will be less than 7. The pH range will be less than 7, which is where this methyl orange will change the color. So yes, the most important thing is it's the titration of a strong acid and a weak base. And then another thing that is important is the pH at the equivalence point will be less than 7, which shows that the acid will overpower the weak base. So yes, that's what you say. Then next they say calculate the concentration of the potassium carbonate solution. Well, this one is really easy. You can use the formula that I said I don't really like. Yes, it's really, really good for you to use in this case. It's short and straight to the point. You don't need to use the stoichiometric calculations. But now this is the most important thing. Can you see that they didn't specify which reaction? No, they didn't say calculate the concentration of the potassium carbonate in run 1 or in run 2. They just say the concentration of this base. So what does it mean? Well, it means that you are not going to use the 20.05. You are also not going to use 20.15, but you're going to use the average of those two. So if you are doing life science, you know this perfectly well, that each time you're performing an experiment, you actually use the average of the readings that you are getting. So yes, let's go ahead and quickly do this one. Well, this is what we say. We said we can use the titration formula. So we can say the concentration of the acid times the volume of the acid divided by the concentration of the base times the volume of the base. This is equal to the number of moles of the acid divided by the moles of the base. And remember that these ones we get from the mole ratio in the balanced chemical reaction. So here it told us that the acid has a concentration of 0.1 mole per cubic decimeters. And in both of these experiments, the runs, we used 25 cubic centimeters of the acid. And remember, I told you that in this formula, you don't really need to convert from cubic centimeters to cubic decimeters. You can just use that. It's perfectly fine. But now we are looking for the concentration of the base. And how do we get the volume of the base? We need to find the average. They didn't specify in which reaction. So we have to find the average of those two volumes. And what is the average? Well, you say 20.05 plus 20.15, and you divide that by 2. Then you find that the average volume will be 20.1. And from this balanced equation, the mole ratio for the acid to the base is 1:2. 1 for the base and 2 for the acid. Yes. So this means here I'm just going to say it's 2:1. Twice as much the base for the acid. Then how do we make this concentration the subject of the formula? Well, it's easy. How is it easy? Well, we just cross multiply, right? We say this one times that, this one times that. And after cross multiplying, we now divide by 2 times 20.1. Then you can now say, therefore, the base here was potassium carbonate. So I'm just going to specify and say the concentration of this potassium carbonate is simply going to be what? Well, let's see. Well, the concentration will simply be 0.06 to 2 decimal places, mole per cubic decimeters. Yes. So we're looking at the last one. They say to us, the above potassium carbonate solution used in the titration was prepared by completely dissolving 6.525 grams of the hydrated potassium carbonate in 600 cubic centimeters of water. And now they are asking us to please find the value of X in the formula that we see above. So I just need you to tell me, what is it that we need to have in order to successfully find the value of X? What is the main thing that we need to calculate? What do you think, Legani? How can we find the value of X? Do you have any idea, Karabo?
I'm not sure, but I think by finding the molar mass.
The molar mass, yes. Thank you so much, Elsie. The molar mass. We need to find the molar mass of the entire compound. Why? Well, that's because they told us that the 6.525 grams, that's the mass of the entire potassium carbonate. Or rather, to put it nicely, it's the mass of the hydrated potassium carbonate. And they also give us the volume of water. And using those two things, we can actually find the number of moles. But not directly, but from the fact that we already know the concentration of this solution. We have already calculated the concentration. We got it to be 0.06. So we can easily find the number of moles. And now that we know the moles, we also know the mass, then we can easily find the molar mass. Okay, I think we can do this one on the next slide. So now we define the concentration of this solution. The sodium carbonate Of course, we know that it's actually bound to X moles of the water of crystallization. So it's going to be defined as the number of moles divided by the volume. Even if it didn't say it's bound to these X moles of crystallization, it's still perfectly fine as long as you'll remember that in the end. So now we have 0.06. We are looking for the moles, but they said this solution was actually obtained by dissolving that mass in how many water, or rather in how many, what volume of water did I use? That's what I wanted to say. 600 cubic centimeters. And if you divide 600 by how much? Yes, if you divide 600 by 1,000, you actually get 0.6. And when you cross multiply, you find that 0.036 moles of this entire compound were actually, I don't know actually what, but that's the number of moles that was dissolved. Now we know the moles, we also know the mass, so we can easily find the molar mass by using this formula. So we have 0.036. We are looking for the mass. No, we are not looking for the mass. The mass is given to us. They said it's 6.525. The molar mass is what we are looking for. If you want to make the molar mass the subject of the formula, you just take it and make it the subject. And you take what was the subject and you make it the denominator. Yes, that's what I wanted to say. So now we know the molar mass of the entire compound. But now it's time for us to carefully analyze this one. How can we find the molar mass of this compound actually? Well, in order for you to find the molar mass of, was it sodium? I think I came up with my own thing here. It's actually potassium, not sodium. It's supposed to be K2CO3, sorry. So now we want to find the molar mass of this one. So we know that we have 2 atoms of potassium, each with a molar mass of 39. 1 atom of carbon, 3 atoms of oxygen. And I want you to look at this X very carefully. This X is the same as 2H2O, for instance. What is the meaning of this 2H2O? It simply means that we have 4 atoms of hydrogen and 2 atoms of oxygen. That's what it means. So, well, you can still keep your X outside. It's perfectly fine. Then you say the molar mass of water is actually 18. Or you can just say it is 18X. That's perfectly fine. Because we have 2 atoms of hydrogen and 16 for oxygen, so it's going to give us 18. And if you now say 2 times 39 plus 12, 3 into 16, you get 138. So you have 138 plus 18x. And this is equal to 181.25. Then when you say 181.25 minus 138 divided by 18 anyway, then we simply find that x is going to be 2.402 and so forth. But your x cannot be a fraction because x is the number of moles. It's like a balancing figure. It has to be a whole number. So then you simply round it off to the nearest integer. And then you say, well, x is going to be 2. Yes, that is what you had to say. And you are fine. You can't leave it as 2.4, so forth. It is an integer, so